Okay, so we're then going to look at this one: A intersection B being a subset of A union B. There, right? We're going to have to prove this statement. So how do we prove this? So there are multiple methods we can use. We can use logical deduction, we can use the analytical methods, or we can use a truth table. But now I'm going to show you how to use logic there. So what do we know here? We know that, okay, this we say let x, right? We're going to say let x, right? Let x be a member of A, right? Intersection B. Then from here now, this implies that x, right, is a member of A and x is a member of B. What do we know from here? We can then say x, we can say for each and every x, right? For each and every x that is a member of A and B, right, comma, x is a member of A, or x is a member of B, or both, right? We have this one here. So you know what, okay, for each and every x that's a member of A and B, x is a member of A, or x is a member of B, or x is a member of both, right? This then implies that, okay, x can also be a member of the union set, right? X is a member of B. Now, this then implies again that x, for each and every x that's a member of A intersection B, right, x is a member of A union B. Also, let y be a member of A union B, right? This implies that y is a member of A, or y is a member of B, or both, right? Then we then say, okay, from this point onwards we can say, okay, y is a member of A, or y is a member of B, but not every y is a member of A and B, right? So for this one, basically by this what we're saying is that, okay, if we have an element y, right, that's a member of the union set, we know to say, okay, this one is a member of A or B or both, right? But also know to say, okay, just because it's a member of A or B, then mean it's a member of both, right? But in the intersection, we know to say, if x is a member of A and B, then it's a member of both, right? Or so it can be A or B or both, right? But for the union, it's not in all cases that it's a member of both. So this basically means that A union B has some elements that are not in the intersection. Hence we can say A intersection B, the subset of A union B. Another way that I personally feel is a bit easier is the table method. So we're going to create a table here. Okay, so now we're going to say A intersection B, A union B, right? So we're going to say, okay, so let's just do table. So we're going to say, okay, we have the element, so this is the numbers here, they are in binary. We're just showing numbers. If we have a 0, it means it's not an element. If we have a 1, it means it's an element, right? So have 0 0 means not an element. 0 1 means this is not an element of A, but it's an element of B. 1 0 1 1. So in the intersection, if you have an element that's not in any of them, of course it won't be in the intersection. If you have an element that's only in B, it won't be in the intersection. If it's only in A, it also won't be in the intersection. If it's in B right? If it's in both A and B, then it will be in the intersection. For the union, if the element isn't there, of course it won't appear. If the element is just in B, of course it will be in the union. If it's just in A, of course it will be in the union. If it's in both of them, of course it will be in the union. What this shows here is that we can look here to say, okay, the intersection set, what if an element appears in both A and B, it will appear in both the intersection and the union. But if it only appears in one of them, it will appear only in the union. This shows us that all the elements in the intersection are also in the union, but not all elements in the union are in the intersection, right? In most cases, which then implies every X that's a member of A intersection B is a member of A union B, right? But not every Y that's a member of A union B is a member of A intersection B, right? So basically here we've proven that this is a subset because all the elements that are in A intersection B are in this one, but not vice versa.